Hello dear friends, this is Sunil Sonigra, and today in the subject of elements of mechanical engineering we are going to discuss the first chapter, that is introduction. Today we will discuss the objectives for today's presentation are: the first one is to understand the application of Zeroth law and first law of thermodynamics, and second, to solve some typical examples based on these two laws of thermodynamics. Previously we had discussed about the basic aspects, the definitions and concept of these two laws. In today's presentation we will understand its application in the field of engineering as well as its examples and typical solution of typical examples based on these two laws. First we discuss thermodynamic equilibrium. What is thermodynamic equilibrium? Let me see with the help of small animation clip. So that is regarding thermodynamic equilibrium, which we studied earlier. Now what is thermodynamic system and properties of system or system properties? Because these two aspects are very important to understand the concept of laws of thermodynamics. Let me see the animation based on the system and its properties.
Systems and discuss the important system properties. Here we're looking at a specific type of system, a thermodynamic system. In a thermodynamic system, we are particularly concerned with the flow of energy and matter. This slide depicts two types of thermodynamic systems: closed systems and open systems. As you can see, both of these systems can exchange energy with its surroundings. However, only open systems can exchange matter with the surroundings. This means that any mass used in a closed system must come from within the system and stays within the system. One question you might ask yourself is Earth a closed or open thermodynamic system? In the next few slides, we will go over four key system properties. The first two are depicted here and refer to the nature of the system. Interdependency indicates the degree of interconnectedness among the subsystems within the system. A spider's web is often a highly interconnected system. If you tug on one part of the web, the tug will be felt throughout the system. Redundancy is the extent to which there are duplicate paths within the system to produce the same result. Compact disks oftentimes have 4 redundant tracks of the same information, so that if there's a speck of dust on one of the bits, there are 3 others which can provide the same information. This is an example of redundancy. The capacity of the system depends on where the system boundary is placed. It also depends on the properties of the system itself. The capacity refers to the productivity of the system. This next property, resiliency, describes the ability of the system to adapt to changes or perturbations in the surroundings. In general, greater redundancy should produce greater resiliency. For example, if the telephone lines to a building are somehow cut, but the building is still connected to the internet, the communication system with the outside world is resilient. However, the trade-off is that you are using more resources to achieve the same result. So these are the 4 properties: interdependency, redundancy, capacity, and resiliency. These four qualities describe the nature of a system. Let's look at these key system properties in another way. C.S. Holling represents adaptive systems as going through cycles in which their properties are represented on these three axes. So this is the same set of ideas but represented in a three-dimensional set of axes. So you can see that the axes are resilience, interconnectedness, and productive capacity. So that's the same three ideas that we were talking about in the last slide. So quoting from C.S. Holling, productive capacity or wealth sets limits for what is possible. It determines the number of alternative options for the future. Connectedness, or interconnectedness, or controllability, determines the degree to which a system can control its own destiny. Resilience, as achieved by adaptive capacity, determines how vulnerable the system is to unexpected disturbances and surprises that can exceed or break that control. So a system naturally goes through a cycle. As systems grow in interconnectedness, they also grow in productive capacity. Economic systems illustrate this point well. Eventually, these systems become highly productive and highly interconnected, yet highly vulnerable to external perturbations. That is, they have a low resilience. So they begin here at a state of low interconnectedness, low productivity, and as they expand their connectedness, their productivity goes up and their resilience goes down. This is the idea that's known as economy of scale. So the global economic system recently illustrated the concept of non-resilient, highly interconnected, high-capacity systems. Many of the developed countries were reliant upon the economic activity of the U.S., so it was highly connected to the system. The collapse of the U.S. economic system precipitated a worldwide collapse in the global economic system. In natural systems that encounter a collapse event, such as a fire in a highly interconnected, highly bioproductive, mature forest, the way they recover from this collapse is to begin a series of disconnected experiments. In other words, they traverse the second dotted line. They go from an economy of scale, in a sense, to the original position where they're exploring, in a way, an economy of scope. An economic analog to this would be an economy of scope where goods and services are exchanged on local levels, drawing from the...
So that's regarding the thermodynamic system. Now let me see some examples based on the laws of thermodynamics and their solutions. The first law of thermodynamics. Say here, consider a system of a piston and cylinder with an enclosed dilute gas characterized by P pressure, volume, temperature and index N. Here a gas is filled up in the cylinder and the piston is moving element, and as the piston moves from upward to downward direction, the pressure of gas increases. So the characteristics of gas is characterized by pressure, volume, temperature and index N. It's like this. What happens to the gas if the piston is moved inward, as shown over here, like this? If the container is insulated, the temperature will rise. If totally the insulated container is there, the temperature of gas will increase and atoms move faster and the pressure rises. Is there more internal energy in the gas? Can you say the internal energy of gas increases? Like this. See, this is delta X, the movement of the piston. External agent did work in pushing the piston inward. See here. Here external agent is there. It pushes this gas. So work is done, which is given by force into displacement. F, the force employed over the piston, is equal to the pressure, which is over here, into the area of the piston. So pressure into area indicates the force of this piston, and delta X is the moment. So W is equal to P into A into delta X. So as we know, P is pressure, area into delta x. Area is this and delta x means this height. So that is the total volume over here covered by this piston. So that is change in volume, so represented by delta V. Hence work done is equal to P into delta V, or PdV work is done over here. Work done on the gas equal to the change in the gase's internal energy as per the laws of thermodynamics. W is equal to delta U, that is change in internal energy. Let's change the situation. Keep the piston fixed at its original location. Say here piston is fixed. Place the cylinder on the hot plate. The cylinder is placed on this hot plate. This is a hot plate. What happens to the gas? So here plate is hot, so heat will transfer from this plate to this gas and the temperature of gas will increase. Heat flows into the gas, atoms move faster, internal energy increases, so internal energy of this gas will increase. Q is equal to heat in joule and delta U is change in internal energy in terms of joules. So by first law, Q is equal to delta U, that is change in internal energy. What if we added heat and pushed the piston in at the same time? If we consider both the things, push the piston over here from this pushing agent and as well as provide heat with this heating plate, then what will happen? Like this. Work is done on the gas. Here work is done on the gas. Heat is added to the gas from here and the internal energy of the gas increases, right? So Q is equal to W plus delta U. Say by employing this force, we are doing work. By heating from here, heat is added and change in internal energy is delta U. So the relationship between these three elements can be represented by the first law, Q is equal to W plus delta U. Some conventions which are used for the gases perspective, heat added is considered as a positive and heat removed is negative. Work done on the gas is positive, work done by the gas is negative. Temperature increase means internal energy change in is positive. So if temperature increases, the change in internal energy is positive, and if temperature reduces, the change in internal energy is negative. Now some animated solved examples. The data is given like this. 25 liter of gas is enclosed in a cylinder and piston arrangement at 2 atmospheric pressure and 300 Kelvin temperature. If 100 kg of mass is placed on the piston, causing the gas to compress to 20 liter at constant pressure. See here the volume is given, that is the volume of gas is 25 liter, and by employing external pressure or external agent, its volume is reduced to 20 liters. So 5 liter volume is reduced, and this is done by allowing heat to flow out of the gas. So heat is allowed to go outside. What is the work done on the gas? What is the change in internal energy of the gas? And how much heat flowed out of the gas? So how to find out the solution of this problem? So for that, let me think the solution. This is the given data. Initial pressure is 202 Pascal, that is 2 bar or 2 atmosphere. Final pressure is also 2 bar because the pressure remains constant. Initial volume is 25 liter. We can convert into meter cube, 0.025 meter cube, and final volume is 0.020 meter cube, that is 20 liter. Initial temperature is 300 Kelvin, final temperature not given. An equation that we know, PV is equal to nRT, so N is equal to PV upon RT. Work done W is equal to minus P into dV. Delta U is equal to 3 by 2 nR delta T, and Q is equal to W plus du. These equations we have derived. Now W is equal to minus P dV. Minus P means the pressure, that is 202,600 Pascal, into change in volume. Final volume is 20 liter, initial volume is 25 liter, so 5 liter is the volume. And by putting the values in this equation, the work done W is equal to 1013 joule energy added to the gas. By this equation we can find out this much energy, 1.013 kilojoule, is added to the gas for this given situation. Now delta U is equal to 3 by 2 nR delta T. So put the values. 3 by 2 means 1.5 into value of nR 2.03, 8.31 into changing temperature, that is minus 60 degrees centigrade. So 1518 joule is delta U, and from the first law of thermodynamics, Q is equal to W plus delta U. W is equal to 1013. So put the values, and Q is equal to minus 505 joule heat out. So this much heat is out from this given situation. Now solving the problems using first law of thermodynamics, let we solve some of the examples based on.
This is video 16.1. In it we'll be solving a problem using the first law of thermodynamics. The question: a gas in a cylinder with a movable piston expands isobarically as 900 joules of heat is added to the gas. Isobarically means that the pressure is constant during the transformation. So if the gauge pressure in the cylinder is 20 kilopascals, the base of the cylinder is 0.4 square meters, and the piston goes up by 10 centimeters, what is the change in internal energy of the gas? We'll start by taking a look at the first law and its contents. It states that the change in internal energy of a gas is equal to the heat added Q minus the work done by the gas. There's some ambiguity, or the potential ambiguity of the sign, because here it's the work done by the gas, and if you were to consider the work done on the gas, you would have to change the sign into a plus sign from a minus sign. As I stated, this is heat added minus work done. So we're going to find the work done. It was stated on the last slide that 900 joules of heat is added, so if we